lesson as we did in the past days, and Professor Bruzzone is not online, so typically he started to record the lesson.
I started the record.
Okay, thank you so much. So maybe Lucio, if you want to just to start from this slide, just to in few words to resume, so that we can cut in this point the registration and start from this point with the material related to this lesson. Thank you, and sorry for this.
Okay, right, no problem. We have just a few minutes extra. I'm sorry, probably I will keep you up until 6:30 maybe today, but I hope it's not a problem for you. In case, just let me know. Right, so let me start this slide again. So I was describing how a viewpoint of a user sees the same system that is seen by a supplier from a completely different perspective. So a user is interested in operational aspects, is interested in those parameters that make sense to him as a user, and defines the performance, for example, of his car by how comfortable it is, by how stylish it is, or how easy it is to drive. So these are the key parameters that matter to the user. The focus is on maximizing performance and minimizing cost. Of course, everybody wants to pay as little as possible and achieve the best performance. This happens for a car owner, it happens for a mobile phone owner, for a telescope users, as we can see in the picture. However, if we switch to a supplier point of view, suddenly the system becomes composed as a very intricate architecture made of components, made of calculations, made of interfaces, requirements, and so on. Not only that, the performance is no more based on those parameters. Parameters are different now. The parameters for the performance by a supplier, as seen by a supplier, are the requirements. I have been given by a contract the requirement to achieve a certain speed, and my car needs to fulfill that. After that, my contract is successful. And of course, I want to maximize my profits, because a supplier is an organization, is a company, is an enterprise that relies on the success of its business. So these different views are important in the representation of an architecture. Let's see how to make that happen. Everything that you will see in the following slides, it's either above or below the horizon, no? Because it is done from that given point of view. So every process, every project, every system, I should say, starts from an analysis of the operational needs of the user. You can see that it's a cloud, a little bit shapeless. It's not square or rounded shape like the others, because it's not very easy to understand which are the needs of the stakeholders. We need to elicit those needs by talking to them, in particular, by doing analysis, and we need to formalize those needs in a document, give a priority, share them with the client. Not only, we must be sure to involve all possible stakeholders for our system. After we have done that, we develop what is called the system concept. A system concept is a first view on some aspects which are relevant for the production of our system. The system concept, of course, is done in close collaboration with the market. I have to consider technologies which are available or that will be in the next future. I have to consider cost-effective solutions and so on. And I have to develop a number of concepts, not just one. The first one is the acquisition concept, which means understanding how the system will be purchased or built or reused. Maybe I'm using something off the shelf that is already stabilized and present on the market. I will just need to make a purchase order and I have a component to use. Or instead I have to develop something from scratch. That's a completely different approach and will have costs and requirements very different. Another concept is the deployment concept, which means how the system will be put in place, how the software will be installed, how the system will be delivered to the country where it will operate, if there are issues in building the system in the operational environment. Another concept is the operational concept. Operational concept means how the user will use the system. So what operations, what activities, what tools the user will have to interact with the system. So it's the description of the operations of the system from the point of view of the user. Parallel to the operational concept, of course, there is a support concept, which means understanding how the system will be maintained operational during its life. So where will I find consumables? Where will I find the expertise needed to use it? Where will I find spare parts? How will I manage accidents or malfunctions? Everything that is not strictly related to the achievement of the main functions, the main goals of the system, but that is in support to them. And finally, how the system will be retired at the end of life, if it will be disposed of or reused or recycled or whatever. So all these things have to be discussed and described much before any system requirement is written. We have the needs of the stakeholders which guide us in this analysis, but we have to understand all these things before we really start. And after that, the next phase is the definition of user requirements. Now we have to formalize those needs in a series of requirements for the system. So we have to start building that bridge that we saw before. This is the first step of building this bridge, of transforming the operational view of the user into a technical view of the supplier. And this is done through this user specification, which is typically the technical base of a tender. A tender is a way from the contractor, the user, to purchase the system. In the international industrial context, it is not uncommon, of course, that there may be direct acquisitions, but typically there is an inquiry over several possible industries, several possible suppliers, in order to promote competitivity and to reduce costs. So there is a tender. A tender is the moment in which the industry makes a proposal responding to the user specification and providing a cost for all the activities that will be necessary to implement our system. The customer will choose one of the supplier and provide a contract. We'll sign a contract, and then at this moment there will be the real start of the definition of the system requirements. So before, there were user requirements, which are also related to the system, but they are seen from the point of view of the user. Now, requirements for the system are expressed from the point of view of the supplier. And the supplier, after starting the project, after having received the contract, will start developing the system. It will start an iterative process of design and analysis and synthesis until the entire architecture of the system has been realized. Later, we will see how to do this step. After the system components have been realized, implemented, we enter a phase of integration of these elements. Of course, the components are built at a lower level of abstraction. Single components are developed. They have to be integrated in a bottom-up fashion in order to reach our system. A system which, needless to say, can be very complex, can be geographically distributed, can involve thousands of sites, every kind of system. It can also be a single mobile phone, and that is as complex as it can be. However, with growing number of components, with growing number of nodes and interactions and users, complexity always increases, and that's where we mostly need systems engineering. So after integration, but in a process which of course is very merged together, we will have system verification. System verification consists in the confirmation that the system does what it was designed for. Of course, this is below the horizon. As we can see, system verification is something that is done by the supplier. So I'm checking that everything that I did, every way I design and built my system is performing well. Is performing well according to what? According to the system specification. So I am confirming that all my requirements have been met and that the system does not have failures. The system has been built right. It is working. It's really doing what I, as a supplier, created it for. However, that's not enough, because at this point we have to cross the border again. We have to go back into the user domain and perform what is called system validation. Validation is different from verification in that this is the confirmation from the user viewpoint that the system does what it was conceived for. So now the system is used in its real operational environment. There will be no or minimal simulations. There will be minimal stubs or mock-ups. The system, when it does its validation, has to be in its real operating environment and possibly also operated by the final user. Now the real question is, did we build the right system? And that's a difficult question, because many times systems that follow perfectly their technical requirements, maybe they will not respond to the stakeholder needs. The question here is, did we build the right system? Of course, the critical phase is all the upper part. In the upper part, if we fail to translate needs into proper requirements, then we will have this type of problems. We may have a system which is performing perfectly against its technical requirements, but the customer is not satisfied. And this is a problem on the long term. I have fulfilled my contract. Yeah, that's right. But maybe the next time the customer will choose another supplier. So as a supplier, as an industry, I had to be very careful that the concept, the stakeholder needs analysis, and the user requirement are really properly defined. Following this,
Lucio, there
yes?
is a question by a student.
Sure.
Hello.
Yeah.
Can you hear me, sir?
Sure.
Actually, sorry for interrupting. I just have a question. When you said that after the system validation, when you said about system validation, you said that there will be at the most minimal or no simulation performed. So my question is, if the system gets as complex as it can, for example, an aircraft. So at that time, is simulation? I mean, is simulation? I think simulation matters there because the system is very complex and. Yeah, so maybe for a less complex system, yeah, I can understand that, okay, the simulation can be minimal or probably no simulation can be conducted. But for a complex system, yeah, that is what my question is. For a complex system, the simulation also plays a part, right?
Let me tell you, of course, there are differences in different domains, but proper validation is always required. For example, in military systems, firing tests have to be real. You are not going to have a military system validated and final acceptance completed if the system has not performed real-life firing. Or a satellite. A satellite has a commissioning and a validation period which can last years, because it is going to happen when the satellite is already on the sky and doing its researches. And the users, the real users, can use the satellite only when it is fully operating. So the truth is that sometimes validation is not really concluded until a very long time after operations have started. So there are different ways in which this is achieved. For example, I have witnessed, we will see also later, transport systems. A transport system like navigation and communication system installed on a bus, the validation is performed on the real streets, on a real line, possibly with students or volunteers who are paid by the company and by the bus operator for this job. But the test must be done on a real street, on real traffic, maybe not on a shorter route, but we are not going to accept the system which has never traveled. So for an aircraft, I don't have direct experience on that, but some real flight tests have to be done. Of course, we are talking about the entire system, which is the airplane, the aircraft. Smaller components may also be accepted in different ways, but overall, the real test of a space equipment or a key flight equipment is accepted after it has fled. Okay, thank you for the question. Does it answer your question?
Yes, sir. Thank you very much.
Right. So after validation, we are ready. Operations and maintenance on parallel follow the system through the life. And of course, that's not the end, because there will be loops from operations back to the design. This happens all the time now, especially with technological systems. Applications, software systems are continuously updated during operations. So while this representation is very generic and can be applied to any system, of course, it doesn't have to be intended as a completely flow down waterfall process. The process is very much iterative and recursive in all aspects. And we will see later also some more about this. Here I summarize the relations between the items. I just point your attentions on what really a validated system responds to. It will respond to the stakeholder needs analysis. If my astronomer does not have the proper resolution for that satellite when it's in space, that's a problem. And even if all technical requirements are met, it can be that we have failed in assessing the proper needs. And this happens all the time. There are many business cases of systems which become obsolete or which fail to understand the evolving needs from the users and which fail their mission. So let's go on. How do we achieve that? How we guide that process of definition of the architecture? Of course, the answer is through the processes. Of course, you have already seen a proper description of all the systems engineering processes, so I will not go in detail. Anywhere, those are the standard ISO 15288.
So, Lucio, just a note about that, and in the previous lessons, speakers focused on technical processes. So if you would like to add something on technical management processes, agreement processes, and organizational project enabling processes, obviously you can say something on this slide.
Sure, absolutely. Well, as you can see, there are 4 categories of processes. First one is it's called agreement processes. These are processes which guide the relationship between different organizations. And no wonder it's just 2, acquisition and supply. Organizations talk to each other to acquire and to supply what? Products, services, or systems. We can call sometime service and consider the system that is providing the service, or we can call a product as a system. No matter what, I'm supplying a system and I'm acquiring a system, or a service, for example. So these are the 2 processes at inter-organizational level. Then there are a number of processes which act at organizational level. These are processes that a company must implement in order to successfully deliver the system. Of course, there are many more than this. There are other administrative and bureaucratical processes. We are not interested in those. These are the processes which have a sense from a systems engineering point of view. So these are the processes that the systems engineer needs to know, even if he will not be the master of these processes. There will be somebody who is in charge of this, better than the systems engineer. The domain of the system engineer are the 2 columns on the left, especially the leftmost one, so the technical processes. So these are the process of life cycle management, so the definition of all the tasks that the engineering of our company has to perform to build and to supply our systems. Infrastructure management, that means managing software, managing computers, managing hardware, managing knowledge, and so on. Portfolio management process is the process that regards how I organize my line of business in a portfolio of products and of systems. Human resource, of course, is easy to understand. Management of competencies and trainings and people. Quality management process relates to the check that everything is done according to the rules that we have established in our company. And the knowledge management process is how I manage the transfer of knowledge and expertise within my company. Then there are processes which are related to a single project. And we see on the right side the technical management processes. These are those in charge of the PM, of the project manager, which are project planning, project assessment, decision management, risk management, configuration management, information management, and quality management. Then there is also the measurement, which is the process by which we acquire information about something, which can be our system or our employees or how we implement our processes. They're a little bit self-explanatory. I don't know if you want me to go in detail with any of this, but probably is not the best thing to do with our short time. Let's say that I'll do it on request. Of course, instead, most important are the technical processes, which are those in which the systems engineer has mastership. We will see them directly on the chart. It's better to do it this way. Why? Because we have to understand how to apply those processes. It's quite a lot of them. You become expert on those processes after years of experience, when you have seen them in place, when you recognize the true meaning of a single process. Of course, at this stage of your knowledge, you have to concern on the theoretical aspects of what is the meaning, the purpose of a project, the inputs and outputs. But I can assure you that you will deeply understand it when you put it in place. And a first thing to understand is the iteration of the processes. In that, as you can see here, we have the first 5 processes which start when a new system is developed: business or mission analysis and stakeholder needs and requirements definition. Soon followed by system requirements definition, architecture, and design. So iteration means that all these processes are held together. There are continuous feedbacks between them. If my architecture is not satisfying, I go back to who developed the mission or the operational view, and I challenge it. There can be updates, there can be negotiations, there can be trade-off. And this is done at the system level. But all of this is done also recursively, going down on the architecture of my system to the components. Why this happens? Well, it happens because there's always a different team doing the engineering of a system level and the engineering at subsystem level. Maybe there is a different supplier. Maybe there is an entirely different company developing in the same project, developing a component, developing a subsystem. So the process of business analysis and stakeholder needs happens again, because if I have a supplier, I am his key stakeholder. I'm his customer. The supplier is providing that part to be integrated into my system. So I am his customer, and he will have to do a a stakeholder needs analysis before deriving his subsystem requirements. So the process is recursive. And to better understand this, there is a construct that is very common in systems engineering world, and that is the V model. V model is the basis for any application of the processes. Have you already seen the V model?
Yes, it was shown to us by other lecturers.
All right. So I'll be very quick on this. The main important thing that I want to show you is, at first, the fact that the typical project milestones are very easily traced on the V. We go from the project financing, so from the moment in which the company has agreed to start a project, to the invitation to tender and contract award phase, we have seen that before, to a system specification, so the system requirements review, which is the review and verification of the requirements we have decided for a system, followed by a preliminary design review that analyzes the high-level design, and the critical design review that freezes, that analyzes the detailed design. Then there is implementation, and after implementation, on the right side of the view, we have test readiness, we have unit acceptance, and moving up, we have component acceptance, let's say temporary, provisional, partial system acceptance after verification, and only after validation, the final system acceptance. So these are the typical milestones. Of course, different acronyms can be used and different number of milestones can be used, but these are just typical. And this is important because we can see how the processes apply to the B model. The technical processes, well, the technical management processes, they start from PF, from project financing, and they go on, let's say, in a way that is rather flat over the entire project. However, the technical processes are more focused on specific areas of the V, which doesn't mean that they are off when that part of the V is passed or before that, but it means that their activity is at minimum. You can see as a normal distribution, no, the effort that is assigned to a process, and every process has its peak in a very specific moment of the V. So the business or mission analysis belongs to, let's say, even before the system is conceived. I'm understanding the business requirements of my company. I'm understanding what kind of mission my department has to perform. Maybe I'm department of a Navy, or maybe I'm a department of Amazon. And Amazon has a mission to implement a new type of service, or to become more socially involved, or so on. So this kind of analysis comes much before a single system is conceived. Then there is the stakeholder needs and requirements definition. So at this point, I go to identify all the stakeholders and identify and analyze their needs. Then I have the requirements definition. Then I have the architectural definition process and the design definition process. The bottom of the V is the implementation, and then coming up, we have integration, verification, and transition, of course. Transition is the process of passage of property, of ownership of the system. The transition sometimes is called commissioning. Is the point when the system is managed by the supplier in its factory, it's touched and operated and owned by the supplier. With the transition, the property and the management of the system is shifted towards the operator, the final operator. That is called transition process. And after that, there is validation. Operations and maintenance are parallel, of course, and finally there is disposal. Right, so this concludes the first part. Of course, system analysis process is analysis process is a very important process. It's critical in all effects. It's composed of studies, of calculations, of simulations, everything that can help the other processes in their decision making, which can help in understanding if the system is performing, if the requirements are met, or anything. So that is the process of system analysis, and it happens, of course, throughout the entire life cycle. Right, so this concludes, no, sorry, there is one more slide, yes. It's a kind of presentation of what is coming next. Of course, in this view, we have to concentrate on this left bottom part, no? Let's say the entire left branch of the V, from stakeholder definition to the design. All this is the concern of this course. And that is what is called developing the system architecture. So the system architecture is a top-down process, and it transforms something as abstract in something very concrete, which ultimately is our system. This will be done through a number of domains. At first, there is a strategic domain. It's the moment where we understand why we are doing things. Then there is the operational domain, which is mission analysis, defining what we have to do. Following is the functional domain, which is the how. Now we start to define the solution, no more the problem. Strategic and operational domain, they are concerned more with the problem. Functional domain is concerned with the solution, and of course, even more the physical domain. The with what are the technologies we are looking for. Of course, in parallel with all of them, there is the requirements domain, which starts at the beginning and ends at the end. So our next 2 hours will be dedicated the first hour to the requirements and the second hour to all the other domains. Thank you. This is all for this first part. If there's any question.
Okay, thank you, Lucio, and we can restart in 10 minutes from now. And if you have any additional question, you can also write on the chat your question, and Lucio will be glad to answer after the break. Okay, so we can restart about 17 past 4 p.m. Okay.
Okay, thank you.
Okay. Hi, everybody.
Hello, Mr. Tirone. We are here.
All right.
So my colleagues, but
can you confirm me that you can see the presentation?
yes, for sure.
Okay. So before we start, maybe we give time to somebody to join. Is there any questions about the first part?
It was all pretty clear to me, Mr. Tirone.
All right, thank you. I was thinking to an interesting point regarding validation. Since I made the example of the car, no? The final validation of the car is no doubt the test drive by the user. When you go to the car dealer, you will never buy a car if they don't allow you to first make a test drive. So that's the final validation of the final customer of the car. And yeah, just to confirm that that process is applicable also to our everyday cases, not just to complex industrial systems. Anyway, we have reached the time, so I start with the second part of my presentation, which will go in detail about the requirements domain. As you have understood, and it is my direct experience, everything starts from requirements. It is very difficult to properly understand it, because we are all engineers. We come from years of performing calculations and algorithms and very complicated drawings and models and whatever. But when we come to what is the reason for failure or success of a system, it is not always, I should say, it's rarely the case that it's the technical skill of all the engineers that makes a product a success. What does instead is the proper management of the requirements throughout the entire effort, from the moment somebody's thinking to build a system with a certain purpose, up to the moment when the system is delivered and sold to the customer and maintained during its life. So requirements are really key. If you go to the root cases of all problems in projects, there are many studies which report as a first cause uncertainty in requirements. So that's the key domain. And let's ask ourselves, what is a requirement? There are many standards. I make this slide almost as a provocation. Whatever textbook you choose, you will have very diverse definitions of what are requirements. I have to say that, yes, of course, I accept all of them, but the one I prefer is much more concise and direct to the point. We will see what that is. Anyway, you will see, we'll have also the chance later to read in the slides. These are all true, and these are all applicable. However, we will see a very simple one later. So in order to move in the world of requirements, we need some standards. I want to list here for you which are the main sources of requirements. One is a very old document, is dated 1994. It's now obsolete, but it's really the basis for all the technical development of systems. It's a military standard, but a few years after it was developed, has also been translated in civil terms. So there are equivalent standards with the same contents. And now they belong completely to the family of standards, which goes under the 15288, as you already well know. I didn't write it here, actually, maybe that's a mistake, but the current standard that includes the same contents of the MIL STD 498 is the 12207 standard, software lifecycle processes, and it's part of the same family of the 15288. Another standard belonging to the same family, you can see the family here. On the page of the standard, you see systems and software engineering. That is the 15288 family of standards. So this one, the second we talk about is 29148. It's called requirements engineering, of course. And the third document, very important one, is the INCOSE guide on writing requirements. These are standards. They're very cold, very just report the basic facts. But here we have a guide. We have an interpretation of how to really write good requirements. So let's see. From the 29148, this is the best definition I have for requirement, which is a statement which translates or expresses a need and its associated constraints and conditions. Mostly, it's a statement. A requirement is a sentence written in a given language, possibly in English, but is a statement. And this statement must be constructed in a certain way. There are what are called patterns for writing templates. They are given in the standard. They are not mandatory. You can use some alternate version, but roughly, a good requirements should be something like this. Let's see the first. It's a condition. When the signal X is received, this is a condition. Or when standard environmental conditions are met, or during night, or in free space, whatever, this is the condition. So when something, the system is the subject, shall, and then a verb, an action. So in this case, the subject is the system. The word shall is there because it's the mandatory words that request something from the subject. And then the action. Action is to set. So this is a function, the function that has to be performed by your system. The signal X received bit within 2 seconds. There is also a constraint. This constraint is actually the performance of our requirement. This requirement is a functional requirement because it has an action. It's at the same time a performance requirement because it has a timing constraint. And all good requirements have both parts. They have a functional part and they have a performance part. The other patterns are very similar. You can see it very clearly. There can be some missing elements like a constraint or like conditions, but still these elements has to be there. Somebody says a good requirements is the one that starts with the word the, because too many times there are requirements that are very funny to read and they tend to lack a proper subject. It's not easy to write good requirements. Well, actually, entire courses can be made on that. But if we follow these rules, we will come up with something good. Let's say the key importance of writing requirements is in this way is that they are testable. If I'm stating a subject and an action, then I can very easily think of a test to prove this requirement is satisfied. If I write something different, like the environmental temperature has to be greater than 50 degrees. Okay, that's a very bad requirement, but it's on all technical specifications, on most technical specifications we know of. Outside temperature has to be above 30 degrees. I'm putting requirements on the environment, on the nature. I cannot put a requirement on that. I cannot say that the environment has to behave in a way. That is part of my context. It's outside of my boundary. What I have to say is what the system has to do in those conditions. So a good requirement is when I say when the temperature is above 30 degrees, then the system shall provide these functions. So it is not so difficult in the end to think of the best way to write the requirements. So what is difficult is to put it in real time, in real life, in real documents which have already been written in a different way, and we have to change that. Anyway, each requirement, as I say, needs a verification method. The verification method is not always a test. Before I was talking about the test to verify the requirement. That's not always the case, and the standard gives us 4 verification methods, which are the ways in which we ensure that the system is verified. These are inspection, that's the first. For example, if a requirement says that an equipment has to be blue, then I'm not going to do any test to verify the frequency of the light and check that it falls into the blue part of the spectrum. I just look at it and say it is blue. So there are requirements which are easy to verify with just a simple inspection. Following, there is analysis. Analysis is when happens when I cannot really prove the requirement because it may be too expensive or because it may be too complex, because it may disrupt parts of the system, whatever. There are many reasons for that. Instead, I can perform a simulation, or I can perform a model or a calculation, and that is considered good enough to consider my requirements met. So analysis is one of the methods for verification of requirements. Another one is demonstration. Demonstration, it means interacting with the system, but in a very simple and reduced way. It means operating the system, but not in a complex and structured way. I don't know, if the requirements is related to a door, I have to open it and close it. Or if it is related to the ergonomy of my laptop, I have to show that I can open it and close it and I can access things easily. I don't really need to have a test environment, a test setup, a test procedure to show that. And finally, of course, the most important is the test. So test is a complex activity, testing, which includes defining precisely what kind of conditions have to be met, what kind of operations have to be done on the system, and what type of equipment we need to interact with the system. So there is a setup, there are procedures, and there is the component. Then we perform the test and we verify our system, our requirements, sorry. Okay.
Excuse me, may I ask a question? I didn't understand if these 4 ways of verification are sequential, so I start with the inspection and then I go on through all of them until the test, or if they are exclusive, so that I choose either the demonstration or either the test, and so like if they are exclusive, and then if they are not exclusive, like they are different, independent, if there are some verification methods that go best paired with one another. So it's useful to do demonstration and the analysis rather than demonstration and the inspection.
Right, good question. No, they are exclusive. You need just one. You need to prove that the requirement is met. And the very important thing, though, is that at the start of your project, and possibly even during tender phase, before you even have a supplier, you are very clear about what is the method that is used for each single of your requirements. So when you write your user requirements specification, you need to know for which requirements you, as a user, as a final user, you want the test, and for which you can instead accept something different. Of course, the ideal would be to have all tests, but that's too costly and impractical, too expensive, and too time consuming. So the very important thing is that there is a mutual agreement between the customer and the supplier very early in the project about which are the requirements that will be verified by test and which by analysis. Why? Because this can have a big impact on the costs of the verification and validation phase. If there are key requirements that I can accept by analysis, it means I have a simulator, like a simulation scenario or a performance of a radar or performance of my satellite. Then, if I accept the analysis, it means that we agree that we don't need a test setup. But if the customer insists and there is a key performance and they request that to be performed by test, they can do it. It has to be contractual, and the supplier will have to understand what is the cost of that. Then, of course, this said, once you have proven a requirement, you don't need to prove it with a different method.
Thank you very much.
You're welcome. Right, and now let's ask ourselves why requirements engineering is necessary. Well, we have seen a life cycle. We have seen milestones in the V cycle, as we remember. The ITT baseline, it's the moment where the technical requirements, the system requirements start to lead. No? This is the moment where I do the tender, so it means I have a specification, the user specification, and I make it public. It becomes official. Well, everything changes. That list of requirements will not remain the same. In time, for example, when there is a contract award, there is already difference. During contract, in several domains, like ship domain or surveillance system domain or military system domain, the difference between ITT and CA can take maybe 1 year of negotiations. And negotiations means that something will change. So some requirement will disappear. We see here, there is this box, the lower one called deleted requirements. Some requirements will disappear. Why? Because maybe during that year of negotiations, we agreed that that is something which is not really necessary, or we have thought of something better. Then there would be instead new requirements. So there would be requirements which were not thought of before, but they show up. We understand that that was a gap because, well, everybody works in tight schedules. So it can be that something was forgotten, has to be included now. Of course, every change that happens has a cost. Nothing goes on without a cost, no? So that is why every modification to a baseline always has attached an impact on time and on cost. But if that is accepted, and typically it is, the baseline will change. So there will be new requirements, and also there will be requirements which were already part of the original set, but which have been changed. And no wonder this happens all the time. This happens when you have a system requirements review. This happens when you have the PDR, when you have the CDR, until the final system acceptance. Requirements change even during the life, even during the validation, but sometimes even during the life of the system. And of course, the more we are on the right of this view, the more we are inside our project, and the more expensive will be any change in our system. So it is better that we do things properly. But mostly important is that we have a very controlled baseline of requirements. Right? And the standard 498 explains to us how to perform that analysis. There is a guidance. I don't want to let you read everything in this moment, but it's things that we have already seen. Actually, all the pictures that you have seen before are in a way an abstraction of the same contents of these words, let's say. So you analyze the user input, develop the concept, the operational concept, plus all the other concepts. Then you define the system requirements. This important part is that when the system consists of sub-elements, this activity must be performed iteratively. This is a key concept. I will show you in a few minutes very well what that means. But there is also another very important part that is done by the 498, which is a complete separation of specification and design. Writing system requirements is done in a document called SSS, which stands for System Subsystem Specification. So the SSS is the document which collects the requirements. Well, it should do only that. In a SSS document, there should be only requirements. So you have a statement about the system asking functions and performance by the system. A different document is the design document. So system design is an activity that comes after that and results in a different document which is called SSDD. Have you ever heard these terms, SSS and SSDD? Are you familiar with that, or are they new terms?
They are new terms for me.
Okay.
Also for me are new.
Okay. Well, these two are the main documents that compose technical specifications. So the SSS is, as I said, a collection of all the requirements of our system. The SSDD is the design description. So it's where I define what are the items, what are the components, what are the technologies that I need in order to satisfy those requirements. So if you want, the SSS is analysis of the problem, the SSDD is analysis of the solution. And it is key that they are separate, because if you mix the two in a same document, you will lose the clear picture of what you need the system for, because you will mix solution elements with the problem elements, and that is something we should not do for all the reasons that have been described to you in the first three lessons. No, we have to concentrate on what I need, not on how I have to, because there may be somebody who has a different opinion and on the solution, and he can fulfill the same requirements in a different way, which can be better. And As a customer, I'm interested in the outcome. I'm interested in satisfying the requirement, not really in what is the solution. If it can be useful for you, coming back to the world of cars, that's simple and easy. When I go to a car dealer and I want to buy a car, I may ask a 4x4 car. So that's not a requirement. That is a constraint. I'm asking a car which has 4x4 traction. Well, this happens. It can be done. It's not new. Happens all the time. But it may be that that company has a car which is just a 2x4, but which has better performance on the type of trucks that I want to go on. So at that point, the dealer should ask me, don't tell me that you need a 4x4. Tell me which kind of mountain you want to climb. And maybe I can have a different solution which can be even cheaper or more satisfactory for your needs. So that's a good example of separating a solution from problem. Right, let's go on. So, of course, design decision remain at the discretion of the developer. It means that if we formalize a requirement and that requirement is satisfied, you don't need to justify the way you did it. If you satisfy all of the requirements that have been given to you as a supplier, then all is done. Your contract is fulfilled. So this is called design authority. This is called having the liberty to choose the design up to the point in which you prove that your requirements are met. Okay? And so let's see how to transform this in really, how to use it in the process of development of a system architecture. So we need a strategy. This strategy has two steps. The first step is the system design strategy, which is what architecture is all about. It is a top-down decomposition of the requirements from high level to low level, and at the same time of definition of the design. This is the first step. We will see it. The second step instead is a reversing of that. We are in the lower part of the V. Now we need to integrate small pieces, small components, parts and bits and pieces, always in bigger elements up to our full system. So let's see how to do it. Well, first, let's consider the word tailoring. You will find many definitions, and according to the domain you are, it can be medical, it can be automotive, it can be space, or it can be computers, whatever. You will find different terms. This is an abstract representation with a level 0 representing the environment, the context of our system, and then a level 1 made by the system, which goes, of course, in parallel with our other systems I'm interacting with. And then there is a level 2. In this case, we use a segment. It can be product, subsystem, assembly, component, part. Whatever it is, it's irrelevant. You just have to apply a tailoring and decide what is your real structure. Let's consider, for example, for the rest of this lecture, that we have a system composed by yellow system and orange subsystem and green component and blue part. Okay? And let's see how it works. This is the engineering. Engineering at system level, now we know very well, starts from contract award. I am a supplier in this case. I don't do anything until, well, it's all very preliminary until I got my contract. Then there are the reviews, and finally there is the CDR. This is when my engineering at system level is complete. Let's consider the subsystem level, so the second level of abstraction. In the beginning, that's completely preliminary because we are still analyzing the requirements at system level. So we cannot really have an engineering at the subsystem level. Iteratively, we define what are our subsystems doing, which we need, and then we will complete the engineering at the subsystem level with a subsystem CDR, which most importantly has to be time-wise before the CDR at system level. And why is that? Very simple reason. If I have completing the engineering of my components, imagine that here there is not just one component, there are not one subsystem. There will be, I don't know, 2, 3, 4 subsystems. If the design of each of them is complete, and then I have problems in their integration, what happens? We are in trouble. So even though we are still before CDR, so we are not really integrating the system, but we cannot afford to have components, to have subsystems which don't interact each other during the test phase. We want to discover it before. So we have to start from the requirements and from the high-level design to understand if those subsystems will properly interact with each other, if proper interfaces are set, if the requirements are matching, and in a way, if the entire system requirements are met. And then I iteratively move down at the lower levels. So when I have the component, I will do the CDR for that component. Preliminary finishes after the subsystem level has started the real engineering. Okay. Now let's change a little bit point of view and watch this same thing from the requirements point of view. The starting point is a system specification. The system specification is the SSS we have seen before. That is a document which includes statements which say the system shall, blah, blah, blah. Now what do I do? Performing the system level engineering consists of doing this operation. The operation is called allocation. So I have the hypothesis of using these two subsystems, A and B. So I have a requirement which says the system, I don't know, let's make an example. The system, it's a radar system, okay? So the requirement says the system shall detect small fishing ships at a distance of 20 kilometers. Right. So that requirement has to be allocated. Now, my radar system will have different components, one of which can be the antenna, another one will be the transmitter, another one will be the screen, and another one will be a database. So when I have the system requirement, I have to understand which of the components contribute to satisfying that requirement. This operation is called allocation. So I identify which are the subsystems which receive as allocation requirements, and then I perform an operation called derivation. What is the derivation and what's the difference between the allocation? The allocations leaves the requirement as it is. So the radar system shall detect the fishing ship at 20 kilometers remains the same when I allocate it to the radar antenna subsystem. However, when I go to write the radar antenna specification, I will have to derive that requirement. The requirement has to be transformed. It will have to take the shape of the antenna shell. So for example, if I understand that my antenna has to be 18 feet or 10 feet, you know, whatever. Let's suppose it has to be an 18 feet antenna. My derived requirement is the antenna shall be 28 feet long, okay? So that is called derivation of the requirement. And in this specification, I collect all the requirements for subsystem A. And I have a different subsystem specification for subsystem B. There will be different documents. And then, no wonder, I repeat recursively the same process. I will allocate my antenna requirements to the components of the antenna. And this time it can be that a component is a hardware component or a software component. These acronyms here are typical of configuration management. CI stands for configuration item. A configuration item is an item about which I have to know exactly the configuration. So if it is version 1, version 1.1 at a certain date. So and of course, about the configuration, about the version 1.1, I need to know all the details. So each component put under configuration control is called a configuration item. So B1 is an hardware configuration item, and B2 is a software, computer software configuration item. So again, that requirement, for example, the length of the antenna, or it could be the power transmitted by the transmitter, you know. In order to achieve that radar performance, the transmitter has to radiate 100 kilowatts of power. So I will have different components, and some of them will receive the allocation of that antenna or transmitter requirement, and others not. And I do the same. I derive the component specification, and I go to component level engineering, repeating the same process. When this is done, top down, I'm not finished. Why? One reason, for example, is tolerances. Maybe here for example, let's talk about the weighting budget. No, I have to make sure that the weight of these two items summed is equal to the weighting requirement for my train, for example. So I may have some tolerance here. And when I go down in the various level of engineering, I will keep decomposing the system in lower level elements and components. Each of them will have their own weight, and there will be, again, margins and tolerances. This cannot be an open loop. When the lowest detail has been reached, I have to go back and verify that all the requirements are coherent with each other, and to verify that all the requirements are met at system level. Let's say this is a verification not done on the system. We are not in the right side of the V. We are doing a preliminary verification on the requirements. So we are checking that our design and our requirements match each other up to system level. Right? Everything clear so far?
Yes.
Very good.
Yes.
So after this is done, of course, we reverse the project, the process. Now we will go a little bit quicker. Some of these things have already been told to you. But anyway, after the system is ready, we do verification starting from the lowest level. So is not the blue here because I just don't have space, but we start at the lower level. We do integration until all the components are ready to pass to the higher level integration. And then after integration is done and all the subcomponents are verified, then we go to verification at the subsystem level. And only when all subsystems have been verified, then we move to verification at system level. Before, we are doing system integration, okay? And again, let's see how this process happens. This is bottom-up, of course. And we start with these two items, the blue ones. What do? We have to integrate these two parts in component B2. So what we do, we take the specification, the SSS of component B2, and we take from there the verification method. This is exactly what we saw before, IADT. Is a test, is it a demonstration? And if it is a test, what kind of conditions are there? And then we perform the verification for all the requirements in the specification of B2. And only then we consider component B2 as verified. Then what do? This is the verification. Then we take another component, B1, which of course has been verified, and we understand that we have to integrate them in some system B. So we take the subsystem specification of B, we acquire the verification method, and we perform verification. Then, after all subsystems are verified, we integrate them at system level. Okay, so the right side of the B is actually a bottom-up approach. Okay, now the system is completely verified and we are ready for validation. And if you see, we have built in another way the same V, which has in its core the requirements. So the role of the requirements is very strong in both sides of the V. When we are doing design and we are moving down the abstraction level of our system, and on the right, because it will provide us the verification methods and the statements of the requirements in the latest baseline in order to perform our tests. Okay, let's move to some specific details in the last minutes on how to write good requirements. Apart from the patterns that we have seen before, there are some rules, some of which I already told you, the presence of the and the subject. In any case, there are other constraints about the requirements. At first, we have to consider that a requirement has to be necessary. We really have to know that every requirement has a cost, because the presence of a requirement requires from the engineer to maintain it, to trace it, and to keep it updated. Eventually, it will require a test or an inspection or some activity to be done. So if that requirement is not there and the system remains the same, then we have to remove it because we are reducing the cost of our system. There are many such requirements. There is a redundancy. There are things which are not really mandatory. So a requirement has to be there if it's really necessary. Then it has to be independent from the implementation. We have seen it before. It should describe what the system has to do. It does not have to describe how. It must be clear and concise. Too many words are useless. It must be easy to understand using really the minimum of words. you often find requirements which say the system has to be designed in order to be able to detect the ship. No, the system has to detect the ship. Cut all the all the redundant parts of the statement. Clear and concise. It has to be complete, so it cannot rely on other requirements. It cannot say the radar system shall detect targets as defined in requirement B1. No, has to be complete. You must be able to read it and to understand what is the test required of that single requirement. It has to be consistent, of course. It cannot say things which are in contrast with each other. And at the same time, of course, must be achievable. We can try to push boundaries of technology, but if something is not feasible, and then we should just not include in our specification. And of course, it must be traceable. So it must be connected to a single element. If a requirement says, for example, the radar system together with the software of the neighboring ship, or together with the command and control of the neighbor ship, has to perform, has to detect a ship at that distance. Indeed, in that case, you are allocating the requirement to two different items, and that is not traceable. It will be harder to maintain traceability. Any change in that requirement may affect another system, and if traceability is lost, the development of that system will have problems sooner or later. Of course, must be verifiable. It is. It must be possible to devise a way to demonstrate that requirement. If I don't know, if I write a requirement on my keyboard and I say that when I hit a button, there has to be a signal moving through a certain path, then it means that I must be able to trace that signal in the architecture of my system without breaking it in order to make the test. Sometimes there are tests that need to decompose the system in order to be performed. Those are expensive, those are useless. You have to think of systems which are growing your system integration verifiable all the time. There are words and terms to avoid. So superlative, you never have to say has to be the highest. Highest than what? That does not have to be subjective language. The most acceptable or the most powerful, or in my opinion, these sometimes you find the requirement sentence that says according to this department, or as agreed during the meeting. No, a requirement has to be technical. You don't have to insert in there language which is related to a single person or organization. They should not be pronouns. You don't have to say the system shall perform this action and then it should do this other. The it is ambiguous. It can refer to another subject in the same sentence. So it is always better to say, always to repeat the noun and not use pronouns. So avoid ambiguous adjectives and adverbs repeatedly, all the time, forever. There are things which should really be avoided. Terms which cannot be verified, comparative phrases. So it should be better than the system that has been sold to another country, and indefinite form. Of course, this is a key, is the English term shall has to be used for mandatory requirements. mandatory features, let's say. Should can be used. Should is used for optional behavior. However, when you use the should, the supplier, the person who needs to verify the requirement, can provide a rationale of why that requirement is not verified. So every time there is a should, that is not mandatory, but you have to provide a reason of why you are not fulfilling that request. And just as a suggestion, must and will or any other thing should be completely avoided. Just use the shall. Of course, there are also conditions on the whole set of requirements. So the whole set of requirements has to be complete, has to be consistent, and has to be economically feasible. Okay, this is all. I leave you with some more extracts from the INCOSE guide from writing requirements. There is much more details on the properties of requirements, on the attributes, and so on. You can just read them after reading the material. So if is there any question about requirements? Okay.
Thank you very much.
You are welcome. So we are going to do another break. Do you agree to keep it short in order to be able to finish the course at 6 o'clock? Oh, Agostino, hi. Nice to see you. Nice to see your mask.
Sorry for being late. I was just joined late because of other meeting.
Right, no problem. So we are going to start our next break. If we could start by 5:15, that would be good.
Ottimo.
Okay. So if there's any question, just leave it in the chat and see you soon. Thank you.
Thank you, Lucio.
Perfect, thank you.
Thank you, Mr. Tirone.
Okay.
back. Can you please confirm that you see the presentation?
Yes.
Okay. Are there any questions about the previous lecture?
You covered all the things that I could think of asking.
Good, thank you. Okay, so I would start so we have proper time to finish, because this part is actually the most difficult to condense in just one lecture. It is well, I've done an operation of distillation of the information I can provide, because it is for me very important to provide you real examples coming from real life. And why is that? Well, it's because these concepts are quite abstract sometimes, because we are all very used in like according to our expertise area, like if we are electronics engineer, using simulation or using PSPICE tools for drawing circuits. You know, that can be as complex as we want, but we are used with that. If you are a mechanical engineer using a CAD or CATIA or whatever, it can be as complex as we want. But if we have to describe an operational mission, an operational activity, or capabilities for our system, that becomes complex. And basically, it is good to provide examples which show the entire process. So that's what I try to do. I try to put examples here. Sometimes I will necessarily have to go very quickly, but just stop me anytime. And I also realized that one of the examples I used is a system that we used as a training, and it has some components in Italian, but in any case, it will be not too difficult to understand that. I can provide any support in translation for this later. So, okay, we have this. We have seen that there are 4 domains to tackle. First one is a strategic domain. It describes the enterprise level objectives that we have for a future system. Of course, we have to start understanding which are the entities involved in our system, which are the needs, we already said, stakeholders, and what are the high-level capabilities that will be required. We don't have to concentrate now on system functions, on specific performance, unless it is a key performance from the operational point of view. I mean, we shouldn't concentrate on technical performance, but on what I really need as a user of our system. So we are going to talk about the system stakeholders, the analysis of their needs, and the analysis of the capabilities. Okay, with just very few examples. So let's talk about stakeholders. You have seen this word all the time from anybody talking about systems engineering, and I'm sure also a big part of STRATEGOS master courses in how to identify, how to understand, how to interface with different types of stakeholders. So let's define it. A stakeholder is any entity which has a legitimate interest in the system. So it's anybody that throughout the entire life of the system can be impacted by the system. It can be, of course, the most simple are the operators. The operators are sometimes even considered part of the system. Sometimes not, but sometimes yes. There can be other users so people who connect remotely with the system and use it. It can be systems which allow our systems to exist. It can be entities interested in the business related to that system. It can be the society as a whole. So there are many types: users, operator, decision making. It can be regulatory authorities, it can be governments, which of course define what kind of frequencies can be used by a communication system and pose limits on that. It can be society in general. Of course, the constant care we have for the environment is very well reflected here, no? Because there are many stakeholders which are passive, which we cannot investigate, which do not have a word in the development of our system. But we have to consider also their concern, and we have to give them word, because, well, the main reason is that any stakeholder is able to provide requirements for our system. So if the system can impact in any possible way as stakeholders, we may be able to write requirements following that type of involvement. So if we know very well, if we are missing requirements, we have troubles. So this activity is fundamental. Then, after we have identified all the possible stakeholders, what do we have to do? Well, we have to understand their needs and write them down, collect them, give them a level of priority, give them an ID. The idea, this is a real life example, a project I made many years ago for European Defense Agency, okay? These were the actual, real, high level stakeholder needs by the European Defense Agency, by other departments inside there. This was a software system installed and internal to the agency, so there was no real environment and users, blah, blah. But still, what we had to do is to try to condense the need into a statement that should not really follow the rules for requirements. These are not real requirements, but still has to be clear and understandable and traceable. And then we provide them a relevance, high, critical, low, whatever, okay? Of course, we have also to understand that the purpose of the system is not to satisfy all the stakeholder needs. From practice, if we think that all the needs are satisfied, well, probably we are missing something. Doing engineering is always a trade-off. There are always conflicting needs. Some stakeholders, they want higher performance, no matter the cost. Some other performance say, no, but I'm paying. And so that performance is not really necessary. So it is not always the case that all the needs can be satisfied. Conflicting needs are always there. Are there questions for this? I heard some noise. No. Okay. So this is about the stakeholder and stakeholder needs, and then capabilities. So we have to identify at high level what are the key high level functionalities in which our system will be involved. Okay, so these are really high level. They are not really system functions, but they are, for example, a navy can consider a ship as the provider of a anti-submarine capability. It can be the provider of a communication relay capability. It can be the provider of a support to search and rescue capability. Okay, so are there questions?
It is clear. Thank you, Mr.
Okay. I heard some background noise, so I have to inform you that I cannot see the chat and the list of participants now. So maybe even if you raise a hand or something, I'm not able to see it. So that's why if there is any noise, I check if it came from any of you. And if there is, of course, questions, please feel free to interrupt me. Okay, so, well, I have to say that's all. The strategic domain, that's all in the summary, of course. It is very a very demanding task to describe properly strategic domain for systems and for fleets and for this kind of level of abstraction. However, in our summary, that's what we put in the strategic domain: stakeholder, their needs, and the high-level capabilities. And then we enter the lower level, which is the operational domain, which is not so lower, I have to say, but it's still something different, because now we are not considering the high-level goals, but we are considering an operational domain. So we are considering a mission. We are considering a given environment in which I have to perform something. So we are describing tasks and activities here, exchanges of information in order to carry out our missions. The integration of this domain with all the others, of course, is very complex. But we will start to see something here. The main items, I put them in order for simplicity, for experience, but of course, that's not always the case. Anyway, a good guideline is to start by conducting an analysis of the mission and of the operational requirements which are mandated for our system. Then to identify the element of the context and of the external actors. We have to define the boundary of our system. That's very important. And I will give you some comments on this later. After that, I have to identify phases, modes, and states. So which are the states of my system? Where a state of a system is not to be considered with a very tight view on the subsystem. Has to be completed, has to be evaluated at the whole system level. For example, a ship. I'm working in a shipbuilding company. A ship can be moored on the dock. It can be moving inside the port, or it can be navigating, or it can be in repair. All these are states, and defining them properly at the beginning of the life cycle is important, because in each of those states, the requirements will be different. So after that, we have to establish performance. So these two acronyms stand for measures of effectiveness and measures of performance. That means the key parameter on the left, MOEs, are understood and owned by the user, and MOPs are measures of performance, are understood and owned by the supplier. Typically, this is of course in some situation there can be more complex definitions. Then we have to transform those operational scenarios into use cases. And this is the last step, because when you have identified the scenarios, the actors, states of the system, the key performance, and we synthesize a number of use cases, we have completed the analysis of the operational domain. The development of the use cases will be already functional domain analysis. So let's see how to do these things. I'll give you some examples taken from my past. So an operational scenario analysis for an air defense system is something like this. Typically a pictorial drawing showing what is our system doing, what is it. In this case, is an air defense. No, I blanked all the things which are classified. it is describing a system which is conceived to protect a facility from air threats. Okay, so in a single picture, with the help of photos or icons or things easy to understand, and with the help of a few definitions, you define the mission for your system. And of course, you can go down in depth many times. For example, these are the operational scenarios this is the operational scenario that we identify for a passenger of a bus transport system. So it's a pictorial. The customer has to understand this. If we come out with a list of functions with a detailed diagram, it will not be able to interact in the proper way. So you have to show that the passenger purchases tickets and travels and plans their trip and call the customer contact center, parks and requests a trip. Then each of these things will become a use case. But as a whole, this picture, we call it operational scenario because this is what happens when an operator is using our system. Maybe they will plan a trip, go to buy the tickets, travel, and during the ride, call the customer center, okay? And soon later, you see the operational scenario from another actor of the system, which in this case is the bus driver. The bus driver has a completely alternative scenario from that of the user of the bus system, which is driving, making an announcement, checking in and checking out when it comes out of the depot at the morning, well, let's say at the start of duty and the end of duty, start emergency calls if any emergency happens, or interact with the support from the control center. You know, so this is what we call operational scenario in that case. There are other examples. Okay. The second point after the operational scenarios is the definition of the context. And that is a key point. That is a very important point. I have a consideration to do here. Many traditional system engineers, so experts of a system, they also do this. They also define the boundary of the system. However, our tendency, our reductionist behavior, our behavior which is aimed to solution, always tends to let us think about defining the boundary of a system through the list of all the internal components of the system. In fact, in many of the specifications of our systems, and Agostino is there, he will have more experience and we will be able to confirm this, I'm quite sure.
Sure.
In many of the specifications, the first requirement is the system is composed of the following elements. Is that right, Agostino?
Is it correct? Is it correct?
Yeah, yeah. Now that is it's too strong to say it is wrong, but actually it is not the optimal thing to do from a system engineering point of view. I will reach a full understanding of my architecture, of the design of the components that I need for my system only after I have performed system engineering analysis for that system. I have to start by understanding what it has to do. And of course, I have to define the boundary. I have to sit on the boundary and look outside of the system, not inside of the system. So in this case, let me show you, this was a very successful diagram in this project. This was a big project. You can imagine where it was looking at the pictures of the customer in the previous slides. No, actually was in Saudi Arabia. The ITS, Intelligent Transport System, is a huge system. It's under development even now, comprises hundreds of bus lines and thousands of buses. And everybody trying to describe the system always made wrong diagrams, including inside the system, for example, the buses themselves. But the point is that the bus is not a part of the ITS. The part of the ITS is all those little machines and screens and buttons and networks and antennas that we put upon the bus. And they are not the system. They are external actors. So when we create the context diagram, you see the ITS is a very small box, but outside there is the whole world. So there are human operators, there are services on the left, so telecommunication, power supply, and so on. There is the environment, the real environment, I mean natural environment, so environment, meteorological conditions and climate and wind and sand and so on. In the lower part, there is all the sites where the system is installed, all the locations that host part of the system. And you can see there is also a smartphone, because inside the system, there are some apps. There are applications for the person to plan their, they're called journey planner, is what we use Google for, Google Maps for. That was part of the system, and that is installed on a smartphone. So the smartphone is outside of my system, and I will be allocated there. And on the right side, there are physical external systems that have to be in contact with our system, like traffic control from different ministries, or the bank system to validate the purchase of tickets, and so on. So this is to let you understand how important is defining the context. And the next few slides show you the analysis of the actors, which can be very detailed. You start from a very high level representation, for example, environment or users or external systems scenario and so on, and then you detail the analysis in a model-based environment by providing attributes and features for constraints for all these categories of actors. All of these are out of our system. Okay, let's move on to the next part, because time is passing. Phases, modes, and states. Well, another very important part, which are, as I was saying before, the states of our system. So if the ship is moored or traveling, or traveling in high sea, or in the dock doing maintenance. There is something to be aware about, which is that the exact terms that we use, which are typically these, phase, mode, and state, they are really arbitrary. We can use one instead of the other. The substance doesn't change. What's important is that a state is a stable configuration of our system, is a stable situation in which our system has well-defined parameters characterizing it. And when a transition happens, the system changes state. For example, I give you an example of a state machine, a real state machine that was done for a military system. It has been declassified in the names, but this is exactly it. And you can see, well, this is the case of Italian terms, sorry about that. But you can see that the top one is long-term storage. The second one is transport. The third one is on-site, and then is deployed, and then operational. All of these states will imply different functions which are active. That means different requirements for our system. Because when I'm in transport configuration, I have vibrational requirements, I have weight requirements, and I have logistic requirements which are completely different from those of when I'm deployed on the field doing my operations. So full understanding in this preliminary stage is to understand what are the states of my system. It doesn't have to be so detailed as to already define all the events and transitions, sorry, between a state and the other. However, it should be suitable for understanding the different possible states of my system. Okay, let's move on to the performance. Performance is another very difficult part. We use the terms MOE and MOP, and several of the standards give a good insight on that. This is the difference that I show you in the first slide, where we saw the car. No, I told you that the car, for the driver, the important parameter is how comfortable he is and how stylish is the car. No, so these are qualitative or quantitative metrics of performance of the system as a whole, indicating the degree of satisfaction by the user. Measures of effectiveness always refer to an entire system and are always above the horizon of the diagram we saw in the first lecture. They are always written from the point of view of the user. Instead, measures of performance, MOP, they are only quantitative. Here we are talking about performance, and they can be related also to subcomponents, and they must be connected to real requirements. Let's make an example. An aircraft in standard climatic conditions must have a maximum range of, I don't know, 700 nautical miles, for example. That's the range of the aircraft. Then I need a capacity of a fuel tank designed properly to respect that that measure. So the capacity of the tank is something which is important for the supplier, important for who designs, but is not so important for the pilot, for example, or even for the air company that manages the flights. It will be important for who manages maintenance, of course. But from an operational point of view, I can have a bigger tank or smaller tank according to the type of engine I've used. What I'm interested with the MOE is the range that I can reach. Okay. And of course, another point is that also measures of performance are dependent on the different phases. You see here those that we call states before, they are called sub-phases. For example, an aircraft during taxi and takeoff and cruise phase. No? Even the MOE can be different in these in the different phases. Consider, for example, the comfort for a passenger. If I am a passenger, I'm mostly interested in the cruise phase. I need to stay many hours in the airplane. I want the maximum comfort here. During climbing phase, that's a phase very short. I agree, there are some vibrations that I will have to suffer, so I can accept a lower performance in this phase here, but not in others. Okay, so that is why it is important to have defined the users, the states, before defining the measures of performance of our system. And moving on, we reach the use cases. So we define use cases because after we have defined all these high-level features of our system, we need to reach a point where functional analysis comes in. And the best way to do this, the best transfer from the operational to the functional domain is through use cases. A use case is a construct that came out with the UML and is also, of course, used by SysML, by which a single functionality of the system is analyzed from the point of view of the operator. So, for example, if I have a surveillance system, as you see in this picture, monitor the environment is the use case by which the operator controls what's happening. So, is a graphical representation with added text to clarify many aspects, and has an identifier, has preconditions, post-conditions, constraints, has a purpose, and has elements on the belonging to a scenario. So actors, triggers, and often also a description of the temporal sequence. Let me give you some examples. We are still back in Saudi Arabia. This is, for example, the purchase ticket at the sales point use case. So there is a passenger that is buying a ticket at a sales point. Sales points is a shop. So there is a staff and there is the shop vendor. The other use case is the passenger purchasing a ticket from a vending machine. Okay, so in this case, there is the bus driver, because there are some buses in which the vending machine is on board, and there is a ticket control staff, which is the people who can control that my ticket is valid. So here, the typical development is to identify which is the main actor of the use case, which are the others, which are the preconditions, post-conditions, the objective, so that's the purpose, and then a sequence of steps. Going step by step, describing what everybody does. It's a high level, of course, and it is very difficult to cover all the possible use cases for a complex system. However, it is necessary because functional requirements will derive from this analysis. Without a good use case analysis, no software nowadays is done. I believe that the use case approach it can be declined in different ways. Some call it user stories. Some call it in agile terms in other ways, but that's the point, is interpreting the functions of the system as something done by through the system by an operator, by a user, and describing that in high-level terms. Okay? Right. Any questions so far? Good. We got 10 minutes left. Sorry about that. I'm already rushing. Anyway, functional domain. Functional domain, from classical definition, is an extension of the operational studies. And now we have to establish if there is a feasible technical approach to our system. Okay? So when we do functional analysis, we are still not sure that all we want can be done. It can be that the requirements are too conflicting. It can be that the technology is not right. It can mean that the software is not mature enough. So functional analysis is necessary to understand all the behavior and functions of our system and its components. So now we start to open the system, go inside and see if all the things that we need to do can be done. And okay, two elements in the functional domain: the structure, logical structure or functional structure of our system, and the system behavior. So I have to understand which are the functions and who they belong to, and I have to understand dynamically in which way they interact with each other. Here we go a little bit more in detail with SysML. I will not, this is not a course on SysML, so I will just give you very high-level highlights. But anyway, when we use SysML, we define the structure, we define the behavior, and put it in relation with the requirements and with parametrics. So requirements, we already know very well what they are. Parametrics are the performance of our system. So these are, they are called the 4 pillars of SysML. And the real value of our model is in all these lines, because all these diagrams, all these pictures, they can exist independently of each other. They can be in conflict. But when we use a model-based approach, we create all these links, and we are sure that something that is written in this diagram is the same as what is written in the other diagram. So, functional analysis means understanding, for example, the ship high-level functions. So now I have a ship. It must provide me combat, safety, command and control, communications. So these are a lower level of the capabilities that we saw before. These are single system capabilities. This is just an example. And this is another. This is a logical architecture. This is a generic air traffic control system. Let's say that is a system that I use for training purposes, abstracting a military command and control system. This is a demilitarized version of a command and control system. For example, sorry again, because these the writings are Italian, but it should not be too difficult. We have a air traffic control system, and below that we have functional nodes, which are the manager of interface, which are the sensor for radar and sensor for IFF, so message-based sensor, the generator of the air picture, the manager of the system. So I am thinking about the high-level functions of my system and collecting them in a logical structures, which means that I'm not thinking of a single piece of hardware. A radar sensor can be any type of radar, can be any brand, can have any power, is just the function that matters here. So it is an entity, functional entity, which interrogates the scenario and extract radar tracks. So this is a functional element that allows me to know what's happening in the area around my my platform. Okay. How we go in more detail about this? Once we have done this, we use two methods. One is called activity diagram to describe the behavior of those logical elements. An activity diagram is basically a flow chart. Okay, is just a flow chart with some semantics showing us the actions that are performed by that element. So I can connect an activity directly with a logical node, a functional node, and describe the behavior of that node. This is an example of an activity diagram for a real-world combat system. Okay, this doesn't need to be declassified because it's very high level, but it's a real one. It was developed many years ago to show that there is a setup of the mission, building the system for the operations, and several activities which, according to the grammar of SysML, they say that these activities under the black line are done in parallel. So during the same time frame, I monitor the status of my links, I synchronize the system, and I build it for operations. And when I have built it for operations, I perform my air defense mission. And during the time, if there is an interrupt, if there is an event from the tactical control operator, the system will go out of this activity and terminate all of them at the same time. This is a typical activity diagram showing a system level behavior. Another tool for behavior is a sequence diagram. Sequence diagram, they do something different. It's no more a flow chart. It's a diagram in which you have the actors as blocks on top of the diagram. So in this case, a dealer and a factory. And then you have a lifeline. You have a line going down vertical with the time flowing in the down direction. Okay, so in this case, for example, ordering an automobile is a sequence diagram that shows us that the dealer sends an order request to the producer, to the factory, and the response to that request, to that service, is the delivery of a car. This is the principle, the basic principle of a sequence diagram. And yeah, this is a message. Lines here are called messages. This is an implementation. An implementation showing us our ATC system, so air traffic control system, the surveillance operator, the air scenario, and the regional control center. This is a real diagram showing how these entities interact with each other. There is a formalization. You can describe states in these kind of boxes. These are messages, these are functions. When you use a model-based approach, your description of the behavior can have a very little ambiguity and inconsistencies. You really can describe effectively what the system is doing. And they also show something interesting, which is this is a system. This is called black box. So this is an example of a black box sequence diagram. I can also show what shape it takes when it becomes a white box sequence diagram, because I can separate my system with the same components that we have seen before. Do you remember there was a system manager, there was a radar sensor, there was an IF sensor, an air picture generator, and the control center interface. So these are the elements that we have seen here in this architecture diagram. Those items, here I described the black box behavior. So I say what the system has to do. And this is a system level requirement. And when I do a white box, I have those elements on the lifeline. I recreate the same sequence. Of course, the interaction with external actors cannot change, but all the internal behavior is defined now and will result in subsystem requirements allocated to the lower system components. So this is the way to derive requirements from system level to subsystem level. Okay, these two approaches, which is better used, activity or sequence diagram? Well, I give some advice here. Typically, I prefer to use sequence diagrams, especially in systems which are message-based, in which the focus is on exchange of information, data, messages, calls, services. That situation is better done with sequence diagrams. Activity diagrams instead are used when you are not really sure about who is doing what, but you have to describe a behavior. Maybe you are thinking of the steps to do, not really thinking of who has to do what. Then you can also reach the same level. Everything that you can do with the sequence, you can also do with an activity diagram. That there is no behavior which requires one of them, but some behaviors are better described with one or the other. And if there are no questions, let's go to the last one. We'll take just a few minutes, which is the physical domain. Of course, we have reached the lowest level. Now we have to find the optimal physical architecture for our system. So basically, we have to do an operation of allocation. That means we have to think now of, well, this is the area that has less support from model-based and from systems engineering, because we are at a point where the engineering domain prevails. So the expert of, I don't know, of electromagnetic radiations will be the best suited to understand the different performance of two different antennas. So the systems engineer role here is to maintain configuration, to maintain traceability, and to ensure that a proper definition of the physical architecture is done, and that everything from the functional domain is allocated to the physical domain. So also here, we have SysML diagrams that help us. In the case of physical structure, we have the block definition diagram and internal block diagram. So these are two different representations of the same architecture. For example, this is always coming back to the air traffic control system, a description of the physical elements. So in this case, I have a subsystem, which is the command and control, with an operational console, with a server, with a radio for data, with the application software and the operation software. We have a primary radar, we have a secondary radar. So this architecture now has become physical, and we do both in the tool and outside an allocation of the functional nodes to the subsystem in a view like this, where I can see, of course, this is a very high level used for teaching purposes, how to allocate the physical, how to allocate the functional components to the physical subsystems of my system. Are there any questions?
Yes, I would like to ask, it is easier in your experience to agree on the requirements with a private customer or an institutional customer? So like with an industry or with some kind of department from some kind of country? And also, which is, in your experience, the hardest passage from the requirement to the implementation? So usually it is the hardest to define the strategic requirement, or it is to implement the physical part of the system, or to pass from the physical to the functional up on the ladder?
Well, both very good questions. On the first one, it is easier when you interact with a private company, I have to say, for a simple reason, which is that normally the scope is lower, is more limited. When you talk with the supplier of a system, they are more used technically in the management of the requirements for their own system, and they know their system very well. When you interact with the institutions or with the ministries or with high-level organizations. There are a couple of things that get in the way, technically speaking. One of them is a hierarchical level which can reach very high. And at that point, technical requirements are very more difficult to convey. No? For example, when you talk with a single company, it's more easy to talk at 360 degrees about their system. But if you go to talk with an admiral in the Navy or a director of Ministry of Transportation, you will most likely talk about a wider system of systems. You will talk about their fleet, about their maintenance centers. So the scope becomes wider and more abstract. So this is one point. Another point is that with some kind of customers, the need tend to become requirements at all costs. So there are clients which are really demanding and fail to see how technical compromise can improve the system. If they have a constraint, if they have something has to be done in a way, it has to be done in that way. So, but that's obvious because well, they're not engineers, no? So they are less used to the trade-offs that reach a technical level. They may be technical. Every customer has a technical department, but the real decision maker can be a politician, can be somebody coming from a totally different background. It's not always a defect. It's not always, even the word defect is not proper. It's not always more difficult to interact, but typically is. So this was the first question. The second one, can you refresh that, please?
I was wondering if, in your experience, there is a specific passage that is harder than the others, so both going down the ladder, so defining the requirements, strategic requirements, or defining the operational requirements from the strategic ones, and also if it, or on the really going up against up the ladder, if it is the hardest point might be in passing from the physical implementation to the functional implementation or the likes.
Right. Well, the most difficult part for me is following the entire process. There is no single step which is harder than the others. It is true that the higher level require more experience, require more vision, but they can also be tackled without incredible problems. The real problems are two, in my opinion, just roughly speaking. One problem is really to follow the entire process. So to start a project where you don't give things for granted. You don't say, well, that's the system, we have little things to do. We already know what the customer wants. Or if you're talking to the customer, I know precisely what I want. So the first thing is to perform the entire process from high level to the low level. That is one difficulty. And another difficulty is to break the habits of who says, well, I have already done things always in this way. Breaking this habit is very tough. So when you understand that a requirement is written wrongly, but it has always been written in that way in the previous specifications, to persuade the owner of that document to change the requirement, sometimes it can be hard. So this is, let me say another thing. Another hard point is to learn when to stop. you can go in modeling and analysis and fixing your model ad libitum, as deep as you want. If you have somebody who enjoys, if you have your system engineer expert in modeling and give him freedom, he may spend the entire duration of the project going always more and more in detail in his analysis. But no, that's not the point. You have to understand when is the proper level that you need at that stage. So when you do an operational analysis, you need to reach the level where you have a clear understanding of the main activities, the main parameters, and the use cases, period. You don't have to start defining every single function and operation and task that you need. So this is also an important part. So know how to balance the effort in the different phases.
Thank you very much.
Okay.
You are welcome. I hope I have answered to everything.
Thank you, Lucio. And I think that we have to stop. And I see Professor Bruzzone that is already ready to end the lesson. I just want to remember students about the final assessment on February 2nd in the afternoon, so the same starting hour. And I would like to thank you all before leaving the stage to Agostino, and thank Lucio for this interesting lesson. Obviously, you now maybe it's just an overview on systems engineering, and there are several things that maybe need to be clarified, and maybe you can use also your thesis if you want for understanding, or maybe go more in details on some topics. Consider that it's not always the case in which you have to develop your system from the beginning, from user needs, from business model to the deployment and so on. But in most of the cases, as an engineer, you will be required to act and to work on an existing system. So to upgrade, to improve, to meet additional rules, regulations, standards, user requirements, needs, and so on. So the problems are even more heavy because you have a system that already exists, and you want to approach the evolution using systems engineering. So in most of the cases, you don't have the design, the clear design, and you have to do reverse engineering for getting understanding on the existing system. There are legacy components that need to be upgraded. So the real life is not so, how to say, clear and as theory. And in practice, you have to adopt your mindset, your engineering mindset to solve concrete problems. And so this is a lesson, and all these tools, all these techniques, methods, and books, standards, and so on, everything should help you in solving real problem. And in most of the cases, it's not even easy to upgrade a system in a way that the system can be still used by consumers or by users without according to new rules or standards that will be required. So now, Agostino, I am happy if you would like to close this module, and thank you again, Lucio, and thank you all for attending, and see you in the final assessment.
Thank you very much, Alfredo. I would like to thank especially today Lucio for the speech. I just attended the second part. However, I really enjoyed it. It was very clear, providing concrete example that I will make it clear the importance to have this approach in a wide spectrum of different problems. Okay, so Lucio, thank you very much. And I remind what you just said, Alfredo, about the exercise that we ran on the afternoon of 2nd of February. This was a set, it was, as was pointed out, was a compact set on system engineering that is wild universe, obviously, and as you have understood, it can be applied almost in all complex systems. So it's a methodological, and let me say, it probably could be even defined a mindset, because it's a different way to work when you are an engineer, that you have this vision, that is the vision of the system instead just the vision of what you do, because usually most of the engineers in the different roles for electrical, mechanical, electronics, naval, etc., they deal with component or subsystem, etc., but often these are part, as we said, of something that is important, that is very important, is capability to interact with the other one, keeping the view of the system, because then the world's performance are much better when you even if you define a single component, if you have the whole system view. And we know, I feel, Lucio, that if I talk about your sector, for instance, in naval engineering, let me say, in the shipbuilding, often very expert company in many different sectors, when they develop a new vessel, they create some let me say, inconsistency that is the result of not getting properly this view, even if in this sector, and the sector of the defense, system engineering is quite consolidated as approach. But even in this case, because the problems are complex, because the company all have, for many reasons, but this still happens. So that means that there is a need to reinforce, and I would thank you very much, you that are part of INCOSE, the society, national society, international society, we had to create this strong synergy with STRATEGOS. Obviously, with STRATEGOS, as was pointed out at the beginning of the speech, we deal, hopefully, our engineer will deal with strategic issues that for sure are, let me say, on the foundation of requirement fixing, for instance, for new system engineering, and so on. But in general, this will be true in a wide spectrum of application, and for sure we needed to transmit this knowledge to our students. Most of the lecture has been recorded. I don't have the second one currently, but I will check with my team if they can recover, and so then we will agree in the way to stream out we can put, and I hope we can continue in this direction. And we will now finish with the final assessment, but and we hope that we will have further opportunity to work together and to cooperate. And by the way, I say to Lucio Tirone, as I was saying to David yesterday, it seems to me, that in case if you are interested, we'll be very glad to have even your own company as partner of STRATEGOS. Currently, one of our patron is a Sistema that is part of Fincantieri group, but in case as a Fincantieri you could be interested, I will send you one of our four. Last but not least, I would like to thank our young engineers that attended. I hope that was another value. I mentioned that I know several of you have examined this period, so the attendance is quite limited in, let me say, in the live virtual presence, if we like to use such strange acronym, but I mean,